Sharing this. Okay, we are streaming and everyone seems to be joining. So welcome everyone. This is Benito Marcote from JIVE, and I'm delighted to welcome you on behalf of the organizing committee of the online seminars sponsored by the European VLBI network and focusing on high-resolution radio astronomy. So today we will have the pleasure of listening to John McKean, who will tell us about how to use VLBI observations of gravitational lenses to put constraints on dark matter models. But first, I would like to start mentioning a few logistic points before we begin. So you will be muted throughout the presentation, but you will be invited to type in any questions that you may have for our speaker, preferably through the Q&A section at any time. Or if you are watching us through YouTube, you can put your question in the chat. We will be watching it there. You will have also the possibility of raising your hand and then just give your question to John by yourself. So please try to write your questions clearly and keep them short because we have the whole seminar within 1 hour. So we will be happy if everyone can actually ask their questions. We will aim to give as many of your questions as we can, but we apologize in advance if your question is not among those that we have time to answer it. Before going to the seminar from by John, I will leave the room to Emmanuel, who will actually introduce our speaker today.
All right, thank you, Benito. So Professor John McKean is the Department of Science, Technology and Innovation of the National Research Foundation, National Facilities of the South African Research Chair Initiative in Very Long Baseline Interferometry, which is hosted by the South African Radio Astronomy Observatory and also co-hosted by the University of Pretoria. He is also a faculty member at the Kapteyn Astronomical Institute at the University of Groningen in Netherlands. Prior to this appointment, he was a postdoctoral fellow and later a staff member at the Netherlands Institute for Radio Astronomy, Astron, from 2009 to 2023. He was a Marie Curie Fellow also at the Max Planck Institute for Radio Astronomy in Bonn from 2005 to 2008, and a visiting scholar at the University of California, Davis, from 2003 to 2005. John obtained his PhD in radio astronomy in 2004 from the University of Manchester in the UK at Bank Observatory. Professor John McKean has extensive experience in multi-wavelength astronomy with a particular focus on radio astronomy. His work spans a wide range of observing facilities from LOFA at the lowest radio frequencies to ALMA at the highest frequencies. He is also a strong advocate for advancing radio astronomy and expanding the global research community, particularly in high angular resolution science, where he leads several large programs on the European VLBI network. His research group develops modeling and imaging algorithms for strong gravitational lenses in the interferometric domain, alongside studies of galaxy formation using strong gravitational lensing. His South African researcher group is also focused on building radio astronomy research infrastructure and capacity across Africa. Thank you, John, and I will hand over the floor to you now.
Yeah, thank you very much. Thank you very much for the invitation and for the nice introduction. Let me just share the screen. Okay, I'm assuming you can see everything fine.
Yep.
Yeah, excellent. Yeah, so thank you very much for the invitation to give a seminar today. And as you heard, I'll be talking about how we can test models for dark matter with extremely high angular resolution imaging of galaxy scale gravitational lenses. Yeah, I have quite a complicated set of institutions, lots of nested acronyms there. So thank you very much, Manuel, for saying them all out there. But yeah, today I'm going to talk about how we can understand galaxy formation, in particular dark matter, using gravitational lenses. I think, if you look into the night sky, if you look at a wonderful image, this is actually an HST image. I keep meaning to update it with a new JWST one. But if you look at the night sky with an optical telescope, you'll see that it's just full of millions and millions of galaxies. These structures have very different colors, different morphologies, different shapes. And really, the key question is how did our galaxy form? And how did these this diverse population of galaxies in the universe form as well? And you'll see the most massive galaxies are typically these spirals down here in the corner, which I hope you can see okay. And the other is these sort of spheroidal elliptical type galaxies, which you can see are quite red. So in this talk, I'll be mainly talking about the properties of dark matter associated with these structures, these early type galaxies. Because those are actually extremely efficient, strong lenses, but there will be some information on or some details on spiral galaxies. So if we put the universe in a box, and this is from Illustrious, you can simulate from reasonably high redshift, say redshift 4, up to so I can just move this up to present day, where on the left you're seeing essentially the optical light, and then on the right you're seeing the molecular gas. And the key thing here is that we believe that structure forms hierarchically. That is, that smaller mass structures are drawn together by gravity to form much larger objects. And what you're seeing also in the sort of top of the panel, the numbers changing, is how the stellar mass of galaxies is growing. You'll see that the colors of the galaxies are changing as star formation occurs. So young new stars are blue, and those older stars appear more red. And you'll see how the star formation rate of the galaxy changes quite dramatically from very low up to just past the sort of the 200 solar mass regime per year. And then if you look on the right side, you can see what's actually happening to the gas. And you'll see there's these moments where it looks like small explosions where the gas is pushed out from those galaxies. And as we get almost close to present day, here at redshift 0.5, we now see that those many small galaxies have merged to form essentially a red galaxy or a massive elliptical galaxy. But not all of the masses are accreted, and we can see there's still some dwarf galaxies as part of the local system. Now, I didn't say too much about the gas explosions on the right side. That's mainly related to AGN feedback and stellar feedback, which is important for galaxy growth, and I won't really be discussing that in this talk. What I'm really interested in is what are the mass properties of these galaxies. And of course, one of the key ideas is that the gravity is what's pulling everything together. And what we find is that the mass of these galaxies is these galaxies are essentially too massive relative to the amount of stars that they have. So we believe that dark matter is extremely important for their development. And so the question is, what kind of universe do we live in? Okay, so if we, instead of looking at the optical layer, the gas, which we can probe using, of course, optical telescopes like HST or JWST, or the gas, which you can probe with ALMA, for example. If instead you were to look at these galaxies through dark matter goggles, and again, this is simulation because we can't directly see the dark matter, then we'll find something that can look like this. So first of all, we believe we live in a cold dark matter universe. This is a very nice description of the large-scale structure of our universe, clusters, groups of galaxies, and even galaxies themselves. However, when you go to subgalactic scales, so these are the small components that are in the vicinity of a much larger galaxy, then we expect that for this cold dark matter universe, there should be thousands of these low-mass dark matter halos around galaxies like our own Milky Way. And of course, the question is, do we see them? And they're very difficult to see because they're dark matter dominated. If instead of living in a cold dark matter universe, we live in a so-called warm dark matter universe, then the amount of low mass structure is suppressed. This happens for two reasons. Essentially, the formation process in the early universe is a little bit slower, but also the warm dark matter halos are also less centrally mass concentrated, so they're more easily destroyed. So you'll see the general structure of the halo looks the same, and you can see it's dominated by this component in the center, but the amount of these low mass structures between these two different models varies quite significantly. So the question is, can we differentiate between these models? And our test is, well, first of all, it's the abundance. How many of these halos do we see? How many of these low mass halos do we see? And then the second thing is what is their mass profiles? And what can that tell us about their formation history? And one of the key measurements is their mass concentration. So from the simulations of dark matter, there is an expectation of what the mass concentration of halos should be. Now, there's also alternative models, and I'll talk about some of those during this presentation. One of them being so-called fuzzy or wave-like dark matter, where instead of dark matter being some kind of thermal relic, some particle and whose thermal energy is maybe frozen in the early universe. Alternatively, it might be some kind of axion-like particle that is something extremely light, whose de Broglie wavelengths can be huge. They can be the order of light years, even on galactic scales. And here's just, again, another simulation comparing what you get from a cold dark matter model with a so-called fuzzy or wave-like dark matter model. And the key idea here is that there will be an element of granularity in the dark matter halos if we, in fact, live in an axion-like particle for the dark matter. So how do we see things which are otherwise invisible? It's called dark matter for a reason. Well, we have to have various indirect measurements, and there are a number that are used. I'm just going to focus on gravitational lensing today, and I'm sure many of you know what that is. But for those of you that don't, what we have is some distant object in the high redshift universe. This is a nice extended radio galaxy with a core and a jet, and some hotspots about redshift 3.2. And then in between that radio galaxy and us is a massive foreground galaxy, which we, in this case, is an elliptical, or a massive elliptical. And then the light gets deflected due to the curvature of space-time around this more massive structure. And our beautiful core jet with hotspots, the object that many of you study, instead gets completely distorted, multiple images form, and then those light rays, you can think of focusing at us on Earth where we can observe them. So what we now see are these distorted arcs, and the shape and the structure of this dark matter halo will tell us will be inferred in the structure and surface brightness distribution of the lensed arcs. However, something to bear in mind is the light has gone a very long way through the universe, and in fact, we're sensitive to all of the mass along the line of sight, whether it be quite massive, causing some sort of shear, or potentially something smaller, which is causing a mass perturbation. So how do we use this to understand substructure? Well, I'll talk about that in a moment. But first of all, I just wanted to highlight something. These are some slides some slides that I received from Richard Parkes a number of years ago, which actually shows how we discovered the first gravitational lens. This is 0958 plus 56, where originally people would be doing a scan of the sky, and then when there's a source, the signal would go up, and then this would go down again when you're no longer in a source. And as you can see, you get some sort of correlated signal from which you can determine the right ascension in this direction, and you can solve for the declination in this direction. And as part of a survey carried out by Dennis Walsh, who was the PhD supervisor of my PhD supervisor at George Bank, they found this a number of objects which they did optical spectroscopy follow-up of. And this object turned out to be the first known gravitational lens. So gravitational lensing actually really started in the radio with the first detection of multiple imaging using, for example, here we have Merlin, where you can see there's two images of the same object. There's image A, there's image B. This is likely emission from the lensing galaxy. And these are extended jets, which are partially lensed, or at least distorted. And then if you increase your baselines again, you go to VLBI, and that's a really nice, nice result where you can zoom in and you can start to see the structure of these images at milli-arcsecond angular resolution. And having this resolution is very important for understanding the properties of low mass halos, because as the mass gets smaller, the distortions get smaller as well. So that's why VLBI is so important. So although the first gravitational lens was found at radio wavelengths, there's only about 30 or 40 known in the last almost 50 years since their first discovery. These are primarily AGN. There is a large number of faint radio emitting quasars and star-forming galaxies, which are also gravitational lens. But when it comes to radio loud or radio bright objects, we're really restricted to in the order of about 35 to 40, which means we're essentially we're finding less than one per year, but that's not quite true. Most of these were found in the 80s and 90s, and then primarily as part of the class survey, which I worked on for my PhD in the late 90s, early 2000s. So here's some examples of some gravitational lenses that were found at radio wavelengths. These are Merlin images at 5 gigahertz of the 22 systems that were found. So here's a nice example of how gravitational lensing works also, where what you have here is a candle, and you have a light source here. And then if you have a wine glass, so here's some wine glasses, if you're looking directly down the wine glass, or through the wine glass to the stem to the base, so if the candle is directly behind the wine glass, then what you see is this beautiful ring, and we call these Einstein rings. The reason being that light can move in any direction around the lens. This is interesting because it tells us that the lens is circularly symmetric, because we have this nice circle. Also, the separation of the images tells us something about the enclosed mass. Okay. Now, if I instead look directly down the wine glass, so instead of looking at it like this, I now look just through the base, and I tilt the wine glass. So now I have an elliptical mass distribution, or elliptical lens. You can see it's more elliptical. Instead of seeing a ring, we now see 4 images of our extended object. That's image 1, image 2, image 3. We can't quite see it, but there's another image behind the stem here. And if I move the wine glass a little bit to the side, then the candle is no longer directly behind our lens here. And instead of getting 4 images of our extended object, we get 2 images of our extended object. And in each case, this separation tells me something about the mass. So this gives you an idea of how the mass and the ellipticity of the lens can be found by just looking at the distribution of the images. Now, of course, what we don't see always is the wine glass, or the base of the wine glass. What we see are just the data, which is the observed candlelight. So maybe not today or just after my talk, but maybe later on, you might want to try this yourself with a candle and a glass with a stem at the bottom. Okay, so I also just wanted to mention a little bit in the theory as well, in terms of how these images form and what information we can extract from them. So the images form at so-called stationary points on the time delay surface. So for this particular lens, this is what we call the time delay surface. These contours are equal arrival time. So here you have a maximum and a minimum, and you have a saddle point and another saddle point. So these saddle points, of course, are a little bit less stable, whereas the maximum and the minimum are much more stable. And at these points, these regions where the images form, we can actually make measurements because that's where our data is. So first of all, there's an expected delay. So the light will have a different travel time due to the geometry of the universe, but it's also delayed because the light passes through the lens. So the time delay tells us something about the potential here. This is the lensing potential. If you take the first derivative of the potential, so this is what we're doing here, then that will tell you the so-called deflections, which are the positions. And then secondly, if you take the next derivative, so if you take the second derivative of the potential, then this tells you something about the magnifications of those images. So the time delays tell us about the potential in the first order, and then we have the first and second derivatives of the potential tell us where the positions of the images should be or what their magnifications are. So if I measure the delay, the positions, or the magnifications, then I can infer what the potential is like. Then here's a final example of how we would use this to understand the properties of low mass halos. And this is sort of what makes lensing unique for this is, so here is an example of an unlensed object, which in this case is a kangaroo. If the kangaroo gets gravitationally lensed, it forms these two arcs. We have an arc, a faint arc here, and then a larger arc. And you'll notice that you can identify bits of the kangaroo that are the same in both. So you can see here's the head of the kangaroo, here's the head of the kangaroo. And then it's got its tail and its feet. I'm going to get confused. That's its tail, and then that's the feet of the kangaroo. So what we have is essentially a mirror image, although it's not identical, but the same information contained in this image should be contained in this image. However, what we also can find is that sometimes one of the images looks different from what it should be relative to our reference image. So for example, the back of the kangaroo here has a little distortion and there's a little blob on top of the kangaroo. So that's clearly not very physical, but it gives you an idea that there's something strange going on here. But what we also have is our reference. And when we look at our reference, we don't see this effect. So this allows us to say that there must be an extra bit of mass in this location relative to some other part of the lens system. And this is a strategy we can use to try and identify these extremely low mass halos because we have these reference images. Here's an HST image of the clone system. Sorry, the quality is not so great. Where you have this is an arcsecond here, so it's a reasonably wide image separation. It's a group system. There's a main galaxy in the center, G1. Then there's two other galaxies, G2 and G3. It's a blue star-forming galaxy that forms this very large arc and a very smaller arc. But what you'll also see is that there's a galaxy G4, and that galaxy G4 is sitting right on the arc. So instead of us having a nice, smooth surface brightness distribution on the arc, it's highly distorted. And in fact, you could argue there's even multiple images of the arc that are formed by this component G4. So the idea is, can we see this for lower masses? Now, as you go to lower masses, galaxies are less luminous, so we might not see the light from this object. And then secondary, as the mass goes down, this distortion will get smaller and smaller and smaller. So there's been some optical work done on this. They're using two systems. This is 1930 and plus 666 and G0946 plus 1006. And in order to model the surface brightness distribution of these two lenses, this is the lens galaxy in the center, this is the lens emission forming these arcs, there has to be an additional mass component, which we do not see any optical light from. One of them has to be there, and one of them has to be there. And this is an order of about 10 to the 8 solar masses halo, and this is something of order 10 to the 10 solar masses halo. So it gives you an idea of the mass scales that we can probe. Now, if you, so if you instead of just so when you do the fitting to the lens modeling, you can say, well, how much extra mass do I need? And there's an example here where there's a little extra clump of mass at this location, giving us our 10 to the 8 halo, even in quite a large mass concentration. And then there's another positive blob here, which we think is an additional mass component of order 10 to the 10. And I just want to say that, this is done at optical wavelengths. Is these results, these detections of these dark halos, these low mass halos have been independently verified by different groups using different data sets, pretty much all the same, like HST or KET-KO. They're using different lensing codes as well. So it's a fairly robust result, something that we're quite certain of. So how do we do this? Radio wavelengths. So here's an example. You have a lens in galaxy. So this is our radio image. You can see here. Sorry, let's go back. So this is our radio images. We have 4 compact images of this object. If we again turn on our dark matter goggles, then you can see there's a high concentration of mass here. That's where the center of the lens in galaxy is. But we expect to see all these other little clumps affecting the overall mass model. And here you can see there's a slightly brighter component, which suggests there's more mass. So the mass of so this particular subhalo will affect this image more than it affects that image and that image. So the fact that this clump is close to this image will change the properties of that image. It'll change its position and it'll change its magnification, and in principle also change the time delay in that direction, but we're not going to talk about that today. These are called flux-ratio anomalies because pretty much all 4-image gravitational lens systems cannot be fit with a completely smooth mass model. So this is saying that the stars, the dark matter, the gas, whatever you want to consider the mass contained within a galaxy, if it was just completely smooth, it was just given by some power law, then we find that you cannot reproduce the observed data with such a model. However, if you start to think about what kind of population of low mass halos would I add, so for example, adding these types of clumps, if you add that kind of population, you can start to put the first constraints or the most detailed constraints on what level of a low mass substructure we have to have in these systems. And of course, we only have a handful of radio lenses, which means we only have a handful, or even smaller handful of useful lenses. So at the moment, we've really just been focused on 6 or 7 systems, which are radio bright. This is the probability distribution. So the probability is a function of the expected mass of the dark matter particle. The black line here is the joint probability, and then the different colors represent different systems. You can see they're actually quite varied. Some look quite consistent with each other. Some are quite different. So, for example, this one here and this one here looks quite different. And if you go through the analysis, you can say, okay, what is the 95% confidence limit on the warm dark matter energy or mass? And the current limits that we have from the radio side are about 5.6 keV, which is interesting, but it's actually still consistent with the CDM value. So as this goes in this direction, you're getting closer to CDM. So how do we try and improve this constraint? Well, first of all, we have to understand other systematics. We're making an assumption that these anomalies, these differences that we're seeing in the images are only purely down to the dark matter. It might be something else. So we're doing investigations of the lens models. Is there variability? Could there be an absorption effect? And I'll talk about that in a moment. So the number also, we only have a handful, but can we go up? We think we need about 150 of such objects in order to give much better constraints. So here's an example. This is our current constraint here with 7 lens quasars observed at radio wavelengths. And then this is what you would get, the dashed line for 30, and then this is what you would get for 130, for example, where this would just move, this peak would just move in this direction for colder models, and it would just move in that direction for warmer models. So the first thing we're doing is trying to understand the systematics. So here's so I have this program called Lensing Over Frequency and Time, which is primarily done using the VLA and the HSA in the US. These are the 6 systems we're looking at. Disk means we believe that it might be a disk galaxy from optical imaging. No disk means that we think it's an elliptical galaxy, but there might still be a disk that we're not aware of. We're monitoring these systems over about 20 visits over the course of about 60 days between 12 and 18 gigahertz. And we chose this high frequency because we wanted to try and rule out some absorption effects. So here's one of the first systems that we've looked at. This is a 1422 plus 231. This was the first system that people actually used to try and identify low mass substructure in lensing halos. This is using Keck-AO. Here's the lens in galaxy. Here's image A, B, C, and D. And the previous radio image I showed you was this object. And if we look at the radio spectra or the flux density as a function of frequency, you'll see that they're just the radio spectra are just completely identical. And this is just textbook case of gravitational lensing. It's the same object. It should have the same radio spectrum. There's a different normalization because the images have a different magnification. But overall, they have the same spectral shape. And we can look at the flux ratios. And if we do that, we see that the flux ratios are just completely flat. So again, this is exactly what we'd expect for gravitational lensing, that the same object is being observed. It should have the same fluxes, therefore same spectrum, therefore the flux ratios we would expect to be constant as well. What I'm actually showing you though here also is these dotted curves, and these dotted curves are the predictions for a smooth mass model. So the relative magnifications of flux ratios, you can see, are quite significantly different. I mean, this is the data. You can hardly even see the error bars on here, but you can see they're significantly different for these ratios, B over A and C over A. They're actually somewhat similar for D over A, but they're still anomalous, as we would call them. So this is an example where we believe that the radio data are sound. We don't think that there's any evidence of a propagation effect or something else. So this would be a very good indicator for the anomaly being due to some perturbation in the mass model. I just wanted to throw this up here. We've measured the spectra over multiple visits. There's not all of them, and the spectra are basically all the same for all of the visits. And you can see the flux ratios are also somewhat consistent during all the visits. So it's not variability that's causing these anomalies either. I'm a little bit tight for time, so I maybe skip this if anyone has any question. This object's also strongly polarized, and we actually see a change in the flux ratio anomaly as a function of the polarized flux. We see a change in the flux ratio anomaly in the polarized flux as a function of frequency, which is quite unexpected. So for C over A, we see that it's basically consistent with what we were getting for the Stokes psi. But when we look at the polarized flux for B over A, we're actually seeing a really strong change in the flux ratio as a function of frequency. And it's consistent when we look at our multiple data sets. This is the polarization fraction on the left as a function of frequency. And then we have the polarized flux ratios on the right. And you can see they're all pretty much consistent. There's a bit of a dodgy observation here that we need to look at. But overall, this is a reasonably consistent result. So it's not due to strong variability. So that's an example where we think that these anomalies must be due to flux ratios, must be due to dark matter. However, here's another example from our program, which is ongoing at the moment. There's another system we call B0128, which has 4 images, A, B, C, and D. There's actually a contour here, which we believe is related to emission from the lens and galaxy, which we also think is a late type or a spiral, a face-on spiral. This is the emission when you subtract off the point sources, or you do a model fit to the different lens images. You can see that there's some emission coming from this 5th component that we believe to be the lens. And when I look at the flux ratios of these images, A, B, C, and D, as a function of frequency, so the flux density is a function of frequency, it's a very different story. Here I'm showing the flux ratio as a function of frequency. And again, we're seeing that the radio spectrum is not the same for all of the images. And also we're seeing the flux ratios changing as a function of frequency. And the reason why this is occurring, we believe, is due to propagation effects. So as the radio waves pass through the lens and galaxy, there is an absorption, and we believe that's due to free absorption in this case. And if you plug in the numbers, then you get a rather high electron density, which is probably affecting image B here, on the order of about 300 to about 3,000 particles per centimeter cubed. The uncertainty is on the size of the disk and a few other things. However, if you go to VLBI, then also something interesting happens. So this is 15 gigahertz VLBI. And what we see here is that image A has this nice little core with a little jet coming out. Image B has quite a lot of structure, and I'll come back to in a second. Image D looks reasonably unresolved, and image C looks reasonably unresolved. Now, gravitational lensing conserves the surface brightness. That means that larger objects are highly magnified, and those have a higher flux density. So therefore, image D and C, which have a lower flux compared to image A, those being more compact and looking less resolved, makes sense. However, what we see is image B is actually much larger, or is certainly larger than image A, which is unexpected because the flux density from image B is actually less than image A. So something has changed the surface brightness of this image. It's actually made it larger. It's inconsistent with gravitational lensing. So is it not a lens? Well, actually, we do know that it's a lens, but what's causing this is scattering likely along the line of sight in the lens, which again, if it being a spiral galaxy with a very large electron density, would make sense. I think there's a little problem here, but I'll have to check it, but the scattering measure on this is huge. There has to be a significant amount of scattering going on between the distant redshift 3 radio source and the redshift 1 lensing galaxy. Now, this was a bit surprising because one of the reasons I did this project at such a high frequency is I was trying to limit the effect of free absorption, but also limiting the effect of scattering in the system. So first of all, I think it's really important to say that there's wideband imaging, and that's something we'll be doing with the SK in the future, and Meerkat in the shorter term. So there's wideband imaging of a larger sample that has VLBI, I think is really needed to understand what is the nature of these anomalous flux ratios, because right now there's an assumption it's only due to dark matter. So for the next part of the talk, I just wanted to talk about what we do for extended objects. So these are what we get for compact objects. Now, for extended objects, everything's a little bit more complicated. Lens modeling becomes more complicated. So what we've developed over, I guess, the last decade or so is a fully Bayesian forward modeling technique that works on the visibility data. And what this does, it determines the best source model, lens model, given the observed visibilities that we get from our interferometer. And of course, as I'm sure you all know, interferometers produce a large number of visibilities. So these are really massive data sets that we're dealing with. So the idea is that we will solve for what the background object looks like. And then if we gravitationally lens it, we have our lens model, which produces the observed brightness distribution, or a model for the observed brightness distribution, which then, taking the noise into account, we can compare with our data. So this is the data that you measure with your interferometer. And then we have our source, which we lens, and then we sample using the Fourier, using the UV coverage, and then we have noise as well. That's our data model. And this is a project, let's say it's been about a decade we've been working on this. We had the first pixelated mass and source model in 2015 using ALMA. It's possible to do simultaneous mass modeling of the lens and kinematic source modeling. There's an example here using ALMA. We have joint lens and source magnetic field analysis, which I'll show a quick slide on in a second. And we're also, partly because of the previous system I was talking about, where the lens code is incorporating scattering and absorption into our model as well. So the idea is that we'll have a sort of single lens code for radio interferometric data that can be used from like LOFAR to ALMA to study various source properties and lens properties. But something you also get from that is a really nice deconvolution. So instead of just using things like clean or multi-scale clean or some variant of the clean algorithm, you actually get the most likely or the most probable surface brightness distribution for the data during this process. So this is the dirty image, or the Fourier transform of your visibilities, and then the underlying model that we can extract from that looks like this. So this is very similar to other methods that I'm sure you're aware of. I just wanted to highlight this nice result that we had this year, early last year in 2025, where there are two lensing galaxies of a distant starburst, which forms this beautiful arc, shown in green here at high angular resolution in terms of the continuum. However, there's also a lower resolution observation of ALMA, which has measured the magnetic field. And when you do the lensing reconstruction, what we find is this distorted arc is in fact a nice spiral galaxy. You can see this nice core area here, and then you've got these spiral arms coming out, and it just looks like almost like N51. It's really fantastic. This is, I think, redshift 3 and a bit. I forgot exactly. It's 3 and a bit. But what you can also see is we can solve for the magnetic field in the background object. So you're getting a parsec scale view of the high redshift universe using gravitational lensing here. You can see it's really nice. The way the magnetic fields look like they're following the spiral arm structure. And again, it just looks like the synchrotron emission you would see from a nearby late type galaxy. I'm a little bit tight for time, so I'll go a little bit faster here. But what we're now doing is saying, well, using these extended systems, what can we say about the mass models of lenses? So this is data taken at about 25 to 50 milli-arcseconds of ALMA. And we can fit our various models to them. And what we're finding is that these simple smooth models, the simple elliptical power laws, we call it, this is the model if you're interested. But to say that galaxies are made of just these elliptical mass distributions is not really working out. This is the foundation of lensing. This is the model that's essentially fitted to almost all applications of gravitational lensing. And what we're now finding using these extremely high quality data sets from, say, ALMA and extremely high quality lens modeling tools that have been developed, we're starting to look at those little differences between that smooth model and that complex model. And this work here, done by Hannah Stacey at ESO, showed that the base factors are of order about 30 to about 120 higher for these more complex models than for, say, the simple power law model. So this is the beginning of trying to get down to what I would call precision lens modeling for various applications. I'll skip this for the moment. We only have a few systems. I just wanted to point this out. This is really nice work that you can do with ALMA. This is a project I have where we're looking at 12 systems at about 50 milli-arcsecond resolution. And I think it's important to see the context here of what these telescopes can do, because I think ALMA is really fantastic, but it doesn't really have enough targets to do this work. And the other thing is it doesn't quite have the angular resolution to really probe to the lowest masses. So how do we do that? Well, we, of course, do that using extremely high angular resolution observations with VLBI. So we typically use the EVN with our telescope here at Hartebistuk in South Africa. And also we use the global VLBI in many cases. We're also using the VLBA. I've missed Hawaii, it's just over there somewhere. And also the phased VLA and the GBT for many of our experiments. This is like and Maryland as well now. So we have like 25, 26 telescopes in these observations, and they're extremely sensitive and have great angular resolution. So first of all, what about wave-like dark matter? So this is some data that was analyzed by Christiana Spingola from INAF for a PhD and has been modeled by Devin Powell, who was a postdoc working in our team. And so this is the really nice VLBI data. And I think Christiana actually gave an EVN seminar on this way back in the beginning when this was started. But I think what we've now been doing is testing what's the granularity of the lens and what kind of axion-like models are consistent with the data. And I think there's a nice way of demonstrating it where this is like some sort of weird lensing signal where you have a very fuzzy, a very granulated halo. And as you change the properties of the axion particle, as you change essentially its energy, you go from something which is very, very distorted to something which becomes very, very smooth. So you can see the sort of lensing curve that we have here is quite smooth relative to something here. But these very disturbed lens models, the source just gets completely obliterated. This does not look like a radio galaxy. So you can solve for what's the most likely data set, or what's most likely, what is the most likely dark matter particle properties that will give us a nice focus source. And Devin in this paper in 2023 sort of demonstrated that you're looking at something in the order of like 10 to the minus 20 EV for an axion-like particle. That's like almost the other end of the spectrum, like the thermorelic dark matter particles of order of a few keV, whereas axion-like particle gives us something of 10 to the minus 20 EV. So it's a very big difference in the mass scale, and they both fit the data not so bad. But I guess what I want to focus on a little bit is this recent detection that we've had. It's something we've known about for a little while, but we've only just recently published because it took us some time to develop the tools to analyze the data at the sort of level that we think it needs to be done for this type of work. So there's a beautiful VLBI image of the object 1938 plus 666, where you can see it has this beautiful, beautiful arc. It was quite bright. When you do the lens analysis, you do the lens inversion, and we find this background object, which gives us this beautiful extended arc. Is almost like a CSO with a separation of about 0.5 kiloparsec or so. So this is like parsec resolution at redshift 2. So it's really, really phenomenal work you can do when you combine gravitational lensing and VLBI. But what's important, in order to make this model work, we actually had to add a small piece of mass. And the key part here is in this region of the image. So for a smooth model that has no subhalo, so if we just simulated what this object would look like if there was no subhalo, then we would expect this to be this nice and smooth. There can be surface brightness variations, but we expect them to be kind of mirrored across this line here. However, what we actually find in the data is this very strong discontinuity. And this discontinuity, we believe, can only be explained by an additional perturbation to the mass model. And then when we include that in our mass model, we find that the mass has to be in the order of 10 to the 6 solar masses. And this appeared in Nature Astronomy towards the end of last year. If instead of just putting down a blob, we can actually use a process called gravitational imaging, which is it's like turning on your dark matter goggles and saying, well, Remember all those little subhalos that we saw in those simulations at the beginning of the talk? Now you're using lensing to infer those objects. Where are they? What is their shape? And this is again the contour of the surface brightness of the arc. And you can see that arc has a little gap in it. Something has caused a break in the arc, just like the optical case I showed you at the beginning. And if we say, well, let's just let the mass be agnostic, it has to be sort of connected, but it doesn't have to be a particular shape, then we find that the object has to sit about here to explain that surface brightness distribution. And what's interesting about this is, well, first of all, in the area where we're sensitive to this type of halo, something of order of 10 to the 6, the probability of finding such a halo for a cold dark matter universe is about 0.65, which is basically consistent with CDM. So the abundance here of this one detection seems to be consistent with cold dark matter. If we have warm dark matter, where the expected abundance is less, then the probability of finding this actually goes down, because it's less likely that such a clump would appear. It's still not, I would say, particularly, it's not ruling out warm and cold dark matter at this stage just based on the abundance, but this is the expected probability for finding such an object for, say, a 4.6 keV warm dark matter particle. But what's actually really powerful about this technique, and what's so powerful about the VLBI, is we can see this by eye. We have, developed quite a sophisticated piece of code to do this, but you can actually see it by eye, and that's extremely powerful. This is the picture we had in our press release, where you can see the optical emission forms this beautiful ring. This is the VLBI emission on top, and then this is a zoom in on the area where the little clump is, which I've shown here in white because it was the only way I could get the color scheme to work. We have JWST data of this system now. It's absolutely incredible, but I'm not able to show it to you today. But yeah, but the really nice thing about having the VLBI is we instead of just saying, well, we find a blob, and we find a blob of this mass, which is much of the work that's been done using HST and other instruments at lower angular resolution, we're also able to fit a large number of models to the data. We've spent a very long time developing the code so that it's sufficiently fast and robust, so we can fit all these models. So in total, we fitted about 25 different parametric models to say, well, now that we know there's something there, what could it be? So first of all, we've tried a point mass, and a point mass you can think of as some sort of compact nuclear object, or say a black hole. And we then tried fitting, say, a King or a Plummer profile that you could say could be a globular cluster. We looked at a broken power law, a broken power law, something that we think would be consistent with CDM, and we also fitted a Sersich profile that would be representative of something which is, say, baryon dominated, so something which is mainly stars and has no dark matter, such as an ultra compact dwarf. And for all these models, we also fitted them with a black hole as well. So imagine you've got a dwarf galaxy with a black hole in it. And this is what we find. So this is the mass we find as a function of radius. These are the different models that are fitted to the data. We're not showing you the data on top of here. We're just sort of showing you what the comparison of the different models. And what we find is that the best fit model is not a point mass, say a black hole. It's actually one of the worst. It's not even a cold dark matter model like an NFW, so again, it's actually one of the worst. But what we find is a uniform disk that has some sort of sharp cutoff at about 140 parsecs. So this is the black curve. It has some sort of cutoff in its mass. So the mass is essentially no longer growing beyond this radius. But what also there needs to be is a central component, which we suspect may be a black hole. But that black hole has to make up about 30% of the mass of that object. So we have something that looks quite strange in the sense that its mass cuts off quite dramatically at about 140 parsecs, but also it must host a rather massive black hole. And if you put that into ChatGPT, it says it looks like this. So you have some kind of dark object. We don't know what it is, and it has some extended mass distribution. This is not an accretion disk. This is gravitational lensing of the stars behind. So there's some sort of extended mass component that's not emitting any light. We have some kind of a dark object that's not emitting any light, and all we're seeing here is the lensing effect of it. But yeah, we don't quite know what it is at the moment. But of course, what we really want to do is try and understand how it compares with CDM or warm dark matter. So if we look at the, I think the key point here, I won't get into the details of this. If someone has a question, we can go back to it. But I think what's important to say is that if you just take what we expect for a cold dark matter model and we fit that to the data, these are the resulting properties of those halos. Although we can fit the model, the resulting model parameters are really quite different from what we'd expect for cold dark matter, warm dark matter universe at the 8 to 17 sigma level. So this would have to be an extremely strange low mass halo if it was, the classical cold dark matter subhalo. And what we're looking at the moment is, could it be more exotic models such as self-interacting dark matter, which I'll talk about later. This paper is now online in Nature Astronomy in case anyone wants to look at it. I think it'll probably get officially published next month, but it's available online in case anyone wants to read the details of this fitting. I just wanted to finish up talking about a little bit tight for time, but I just wanted to finish up talking about a couple of things. You might notice I've only spoken about a handful of lens systems. That's really because we just don't have enough candidates right now. So in the future, we expect the SKA, when you combine it, and also LOFAR, I should say, when we combine that with the optical surveys such as LSST, and I'm one of the South African PIs on the LSST project, we're expecting to find about 10 to the 5 lens radio sources, which in principle could be used for some of the techniques we have described today. And I just want to show you this a nice example of the data. Here's the optical galaxy from the lens, and then here is the lensed images you would detect with, say, something like the SKA. But what we really want to do is do VLBI. We want to find more halos like the one I've just spoken about, because they're extremely powerful for ruling out models for dark matter. So what we've also been doing is work done by Dio, who's part of our team, where he's been simulating what you would get for the object that we had already using a so-called actual African VLBI network. And by actual, I mean something which is probably quite realistic in the short term. That is, we have Meerkat, which is now available for VLBI. There's the SK MPI dish, which in principle can be used for VLBI. And we have the harpistic 26-meter telescope near Pretoria. There'll be a telescope, hopefully soon, be constructed in Botswana. There is the telescope in Ghana, which is almost VLBI ready. And in the next few years, we will see the EMT be delivered, and that will also be possible to use for VLBI work. So we've done a small simulation. This is the UV coverage. This is what you would get. And actually, with this type of telescope, we would actually see a little deformity in the arc. So such an array would actually allow us to detect this 10 to the 6 halo. And Dio's been looking at different fluxes and various other things to see where we could, what type of objects we could detect. This work is ongoing at the moment, but it looks quite promising that we can find hundreds of thousands of lenses with the SKA, and then in principle, we'll have a VLBI network where we can try and find more of these low mass halos. So this is our team. Actually, Zane is now left. He's now doing a PhD in Durham, and we've got a few more students who have joined. But of course, the idea is we want to have loads of telescopes in Africa, so that we can connect with the SKA and also connect the European VLBI network and the Long Baseline Array in Australia. So we have this concept called VLBI under the African sky, where we are hoping to form this African Center of Excellence in VLBI that can really push the field on the continent of Africa. This means developing an educational program as part of the research chair, which I have. This will be Africa-wide BSc and honors program, potentially be a virtual classroom. There's training and expertise via radio astronomy and VLBI schools. So there's the ERIS school that I'm sure many of you are aware of. Oops. We also have we also just had the Surveyo African VLBI school. We're also developing the research program on the continent of Africa and how high resolution studies can really unlock the radio universe with Meerkat VLBI and our Hartobistic telescope. We're also developing and looking into instrumentation. So how can we have the hardware, the proper receiver systems for VLBI, and also looking at software analysis tools. This is work led by Jack Radcliffe, such as developing pipelines that we can use for such a system. And of course, we want to have this institute. We want to have this institute of national, international impact that can really collaborate with what's going on in Europe, China, and the US and Australia as a sort of hub for VLBI in Africa. So I just wanted to finish off by mentioning the EVA. I think it's really important, obviously, with my current position. This is people sometimes say, "What is the VLBI network?" And what I'm telling them is that the VLBI network does exist. We do have telescopes which are being used for VLBI operations such as HART and Meerkat with the EVN, but there's a network of people, and I think that's something which it really needs to be looked at. We just had our first Surveyo African VLBI school with about 35 people last year. And the hope is that these people will lay the groundwork for the VLBI community in Africa going forward. But if you're interested in being involved in what we're doing, then just reach out to me. So I'm ridiculously over time, I think. So I'll just leave up my summary there. And if anyone has any questions, I'll be happy to answer them.
Thank you very much, John. It's been a great talk. And it's really good that you also highlight everyone that is behind. It's not only about the results, the instruments, but also the people around. And it's also great to combine really great science and when you can actually show really beautiful and nice images at the same time of the science. Like that's not quite often the case on VLBI, so this is really great job. Thank you. So with that, we will open the floor for questions. So if you have any question for John, please, you can raise your hand if you want to say it. Otherwise, use the Q&A section to write it down, and then we will make the question to John. And if you're in YouTube, you can also leave it there in the chat. So we will monitor the three parts. So,
I have a question while if someone is writing for John. John, you showed these polarization images and how you can reconstruct the spiral arms of the galaxy with the polarization lines. Would you say that measuring rotation measure could add significant value to the analysis? So is the signal being distorted in different ways affects rotation measure differently, and you can extract more information from that?
Yeah, so that was actually kind of the goal of Simon Indurito, who was a PhD student working with myself in Groningen, and also an MPA with one of Vegeti. And because a lot of people actually are interested in what's going on in the background source, but we were interested in these foreground effects because it can tell us something about the ISM, which may also be affecting the flux ratios that we were talking about. So the main goal of actually developing that piece of code was to be able to try and recover the electron density along the line of sight and also the magnetic field along the line of sight in these sort of spiral lenses. So it's been really nice work done by Anne Mao and her team that had these point sources that showed the change in the RM. Because gravitational lensing conserves surface brightness, which means the Q and the U are conserved, which means the angle is conserved. So the angle is not changed by gravitational lensing. You have this idea that, an arc, something which is like this becomes arc. So the polarization angle must change as well, but it's actually not what happens. The polarization angle is an intrinsic property. So if you do see differences in the images, that's telling you there's something along the line of sight which has affected those images. And I think Anne's done some really nice work putting constraints on magnetic field strength of spiral galaxies. But that was using point sources. And what we've tried to do in the development of our code is to do this for extended objects because you get much more information. I didn't really have time to talk about it today, but I think Simon had a paper on it last year where he sort of showed that you can do a reasonably good job of recovering the model we put in, depending on the quality of the data. But the example I showed you, which I can go back to if you like, that was actually the background object that we reconstructed. So instead of doing something at redshift local, you can use this technique to go to very high redshift. And we're thinking about how we can use this for the SK as well. But ALMA has become really interesting for this because dust can be quite reasonably highly polarized.
Yeah, great, thank you. Benito, do you see any other question in YouTube, for example?
Not for now. I had one question actually, just because I don't have the time scales in my mind. So what's the chances and what happens if you have, because in some cases you may have a flaring blazar also as background source, which we know. On your time scales you can have some flaring activity there. If you have one of these gravitational lenses, it will help you to trace back in a much thinner detail the lens itself. But then I'm not sure what's the correlation, what's the time scales that you will expect to see that flare across the lens.
Yeah. So you're basically seeing one image flare, then another image flare. Is that what you're meaning? Yeah. So we call this the gravitational lensing time delay, and there's two bits to it. There's the there's angular diameter distances, whereas cosmology. And so as the images get further apart, that means there must be a larger path length that light has gone. So that's the first thing. The second aspect of the time delay is that as light passes through a gravitational potential, it will slow down from GR. And so you have those two things which you can combine. Now, I don't want to say typical, but it's days to months, right? So it depends a little bit on the image configuration. If the images are very close together, like we have merging images, like I showed for 1938, the VLBI, so if this is flaring, because the images are very close together, then the time delay will be very small. So that would be like hours. Whereas when the images are very far apart, it can be, it can certainly be many months, it can be years, and for clusters, which are massive, and the images are it's a very big path length, they had to go a very long way around the cluster. Those can be many years. So yeah, I think Christiana Spengler has been doing a lot of really nice work on this, looking at flaring of lensed blazars. Most of the time delays that we have at radio wavelengths, which is again just a handful, is from these very strong blazars at 0218, Parks 1830, for example, are the classic ones.
Okay, but that's observable times. Actually, that's really interesting.
Yeah, but and also like I said, the time delay is dependent on the potential. So if you have a small change in the potential due to one of these subhalos, that will also change the time delay, but you have to have ridiculously good time precision. And if only we had something which flared on fractions of a second that's lensed, then we would be able to do that type of work. So for example, a lensed FRB would be extremely exciting for that type of work. Yeah.
Thank you.
Maybe you should aim to measure an FRB through a lens.
Yeah. That's something we would love to see. As more FRBs are found. I don't believe there's a lensed FRB found at the moment. I think there's a few candidates, but I think a lensed FRB would be really exciting. But then there's other aspects, there's other complications, but still seeing you would have a ridiculously accurate time delay at that point.
Benito, we have time for one question in the...
Yeah, maybe let's do that question.
Okay, I can read it from Thomas Crisman. If the VLBI target is varying during the observation, for example, because of scattering or intrinsic variability, could this cause a gap in the brightness distribution of the lensed ring?
Yeah, you could actually get something like that. So if the object was varying extremely large, extremely fast, then you could get that gap in the arc, because the images temporally they're actually different. That was the point we were trying to say, is that there's a time delay across the different images. So yeah, if there was a high scattering event, then the image's properties could change at a very small scale. In terms of this particular object that I brought up, and the gap in the arc, we have multiple frequency observations over different epochs. It was just observed again with the EVN a couple of months ago. But when we look at the multiple epochs and the multiple frequencies, the gap remains. So I don't believe that it's due to a single scattering event. The other thing is, as well, is that the general brightness of the arc doesn't look like it's scatter broadened to me.
Okay, thank you very much. I think we will conclude here to don't go too much over the hour. Before finishing, I will just do a very quick announcements. First, we already have the next seminar, which will be Rocco Lico from INAF, and he will basically tell us about NOVI and how to trace the outflows from these NOVI events via VLBI. And then the last one is that in September, we are organizing the EVN Symposium, a users meeting that will happen in Manchester. Emmanuel, that it's here as organizing of the seminars, is one of the main organizers of the meeting. So we will be happy to see you there. We will discuss all the science that has been done on VLBI and that affects other fields. And then we will have the user meeting where all the users for EVN, you can meet everyone that works on the observatory, and we can hear about it and get the feedback there. So with that, I will thanks John for the nice seminars and everyone that attended. So thank you very much and see you next month.